We're going to continue to look at right triangles and some applications of right triangles that we haven't looked at before. And the applications that we're going to start with are applications of navigation. Now, when we talk about navigation, we usually are referring to the bearing of an object. Usually it's a plane, a boat, a satellite, something like that. And basically what the bearing is giving us is the direction of motion of an object. Now there's two different ways to talk about bearing, and I'll give you the first description and then we'll work an example using that first description, and then the second one we'll work an example as well. So in expressing bearing, we can do it simply just with angles, or we can use it with angle and direction. So our first method will just be with angles. Now with this one, what ends up happening is we use this when a single value of an angle is given. So if there's no north, south, east, or west, it's just a single angle. And when this happens, it is understood that bearing is measured in a clockwise direction from due north. So what we do is we draw a vertical line, and the top of that would be due north. And then we measure from there in a clockwise direction. So this doesn't actually always end up looking like a triangle per se, but usually after we draw this out, we can get a triangle out of it. But right away it might not look like a triangle type of problem. So the problem I want to work, we'll use this particular method. So let me pop it into here. And these are long problems. There's a lot of steps to them, and so they do take a while and they take a lot of paper, but I'm going to make sure I don't skip any steps, so that way you won't ever have to look back and wonder where something came from. So the first important thing we need to do is to draw a picture that describes this situation, and then from there we'll try and solve. So we have radar stations A and B are on an east-west line, 3.7 kilometers apart. So let's go ahead and first start with that. So we have station A, and then we have station B, and then they're on an east-west line. That means they're on a horizontal line. Okay, station A detects a plane at C on a bearing of 61 degrees. And so there's no north, there's no south, east, or west. So what I need to do is I need to use this single angle. So when I use this single angle, it says it is understood that the bearing is measured in a clockwise direction from due north. So what I'm going to do is I'm going to go ahead and sketch in a due north line from this radar station. And at the top of this due north line is north. Now it says that station A detects plane C on a bearing of 61 degrees. And so what happens then is from counterclockwise from here is 61 degrees. Okay, and then what we have, it says station B simultaneously detects the same plane, and so over here we have station B. I also have that north-south line that I want to look at. Due north is at the top, and it says from station B I detect the same plane on a bearing of 331 degrees. So I'm starting here and I'm going around 331 degrees. Well, here's 90 degrees, here's 180 degrees, here's 270, so let me mark those in. So it's 90, 180, 270, and then I need to go up to 331. So if I'm at 270 right here, 331 would be another 61 degrees. So I'd move up another 61 degrees. And along this bearing, is where they both cross, right up in here. So this is 61 degrees. The total amount of rotation here is 331, and again, I'm moving in a counterclockwise fashion. So if I look at this, and I'm trying to figure out exactly what's going on here, I should be able to fill in either a couple more angles or a couple more pieces of information and find the distance from A to C. Now C is right up here, is where that airplane is. So I want to find that distance from A to C. So let's see if we can figure out anything that's going on here that would help me try and solve this problem. Now they do tell me that these two radar stations are 3.7 kilometers apart. So that's something that kind of helps us out a little bit. So I have an interior angle and I have one side. You know, I'm not real sure. Can I use SOHCAHTOA on this or not? I don't see a 90-degree angle right now. So let's find the other angles to see if there is a 90 involved. Well, this makes a 90-degree angle right here. And if I know one of the angles is 61, the complementary, or the angle that's complementary to that, is 29 degrees. Now if I add up 61 and 29, I get 90 degrees. So that must mean 90 degrees is left for up here. So this is my 90-degree angle. So the hypotenuse here is C. And then this is side B because it's opposite angle B. And this is side A because it's opposite angle A. So I should be able to set something up here. Now I want to find B, and I know the hypotenuse, so that's going to either be the opposite or the adjacent in the hypotenuse. It's not going to be opposite and adjacent for tangent. I want to know B, so I could use cosine of 29 degrees is adjacent over hypotenuse, or I could use sine of 61 is opposite over hypotenuse. I should get the same answer either way. So let's go ahead and set this up. Let's do the sine. Sine of 61 degrees. So that's sine of 61 degrees is opposite, and this is hypotenuse. So here I have the sine of 61 degrees. Opposite side is my unknown side. Hypotenuse is 3.7. Now if I want to solve for B, I'd multiply both sides through by 3.7. And these would cancel. And I'd get B equals 3.7 times the sine of 61 degrees. Now I don't want to round anything until I get to the very end here. So let's go ahead and pop in that calculator. And so I'm going to have 3.7 sine 61 degrees. And I don't have to put the degree in because I'm in degree mode. I should always double check that, but I'm going to put the degree in just so I remember that I'm in degree mode. So I get 3.236 3.2360929, etc. kilometers. And then in my math lab, it'll ask you to round that to, let's say, tenths, hundredths, or thousandths. I'm just going to leave it like this. I want to set up the same exact problem now using the cosine. So I could have used the cosine of 29 degrees and used that adjacent leg, which is my unknown leg, and the hypotenuse, which is 3.7. Now the reason this is going to work is sine and cosine, if you recall, are those, what did we call those? Those co-angle pairs. And 29 and 61 are 90 degrees, so they're complementary. So what ends up happening is the cosine of 29 and the sine of 61 are the exact same value. So let's see if that actually works. So if I multiply both sides by 3.7 to clear that fraction, I end up with B equals 3.7 cosine of 29 degrees. So let's go ahead and plug that into the calculator and see what we get. So I get 3.7 times the cosine, not the sine, but the cosine of 29 degrees, And again, I like to put in the degree just so I remember I'm in degree mode, which that shows up here. And you can see that I get the exact same answer. So it doesn't matter if I solve this with sines or cosines, as long as 609 kilometers, as long as you can set up the triangle is the important thing, and then you can choose from there based on the information that's given. So sometimes it's easier to solve one over the other, but sometimes it just doesn't matter. And in this one, it just simply didn't matter. Make sure when you round these as per the instructions in my math lab. Seems like each problem is a little bit different. Okay, so the next one we're going to do is we're going to express bearing using a second method. Actually, I want to run up here real quick. I'm going to insert some space here. I kind of feel like I should have given some examples here of that. So I'm going to show some examples of that. So if we express bearing using this method, some examples would look like I'd have a north or a south. I'm sorry, I would just have a degree. I want to make sure I'm looking at the right one here. So I just would have a degree bearing on this north-south line. And then what I do is I go counterclockwise from that. And so I'm moving in the counterclockwise direction. And let's say this one is 50 degrees. So this particular example would just be, as it shows, 50 degrees. Now if we looked at another one, I always start with north. I'm going to go counterclockwise. And I'm just going to put in this horizontal line to kind of help me keep track. There's 90, there's 180, there's 270 if I went all the way around. But this is just 200 degrees. So if I said 200, I'm bearing 200 degrees, this would mean starting from the north, I'm going 200 degrees counterclockwise. And then this is the problem that we work that goes along with that. I'm going to insert a little more space here. If it will let me. There. Okay, now the method 2 that I want to look at is going to use north, south, east, and west. So this method 2 what I do then is I start with the north-south line. So it kind of looks a little similar to what we were just working on, but before I just had a north bearing north, true north line. So we start with the north-south line. And then what we do, we use some acute angles. So we use acute angles. To show the direction. Either east or west from this line. So for this one, what it ends up looking like is it ends up looking like saying north or south, you get to pick, and then some acute angle, and then east or west you get to pick depending on the situation. So a couple of examples that we could look at here then are something like, here's our north-south line. So we would say we're starting the north, and then we go 50 degrees east, because this is heading off east. So we have a north-south line. This one is heading south. This one's going east. And then again, I want an acute angle. So the acute angle here would be 80 degrees. This one was 50 degrees. And it doesn't matter to me whether it's positive or negative. The east or west takes care of that. So this would be south, 80 degrees east. Okay, let's look at another one. So this one's heading south and then it's going west. And we'll say from here it's 100 degrees. And again, it has to, I'm sorry, 10 degrees. It has to be an acute angle. So 100 degrees would not be an acute angle. So this would be 10 degrees. So what we'd say is south, 10 degrees west here. So that's our method 2. Now from this method 2, let's go ahead and look at a problem that you might run into. Okay, so we have a ship here that leaves port and sails on a bearing of north 47 degrees east for 3.5 hours, and then it turns and sails on a bearing of south 43 degrees east for 4 hours. It says if the ship's rate is 22 knots, a knot is a nautical mile per hour, find the distance from the ship that the ship is from the port. So notice it's not just a degree measure here, it's the north 47 degrees east. So I need to follow my instructions up here, and I have to start with the north-south line and use acute angles to show the direction. Okay, so let's go ahead and start on this north-south line to get us started. Try to be more straight than that. Might be a little better, I don't know. And here's our port. So I'm starting here. Now here's north and here's south. Now from the port, it says my bearing is north 47 degrees east. So I know I'm heading out 47 degrees east. Okay, and then it says I turn. So at this point I'll say I turn. And when I turn, what ends up happening is I have another north-south line that I need to work with. Now as I turn, it says 43 degrees east for 4 hours. Okay, so 43 degrees east as I go south. So from this south line, I'm going to head east this direction of 43 degrees. So this is 43 degrees right here. Now it says, find the distance that the ship is from the port. So here's my ship now. I traveled for 4 hours in that direction, and there's my final location right here. So what I want to figure out is the distance from the port to the ship. So that's this distance right here. Okay, and that'll go from this point to this point right here. Well, I can find that distance if I knew some more about my angles. Now this, I can't say that this is a 90-degree angle right here, because I don't think that this angle in this distance is obviously a 90-degree or anything like that. So I need to kind of figure out what's going on here. However, these north-south lines are parallel. So I have two parallel lines cut by a transversal, and then what happens are alternate interior angles are equal. So this I'm going to call 47 degrees because this angle and this angle are alternate interior angles. So now I have a 47 plus 43, which would be 90-degree angle. So this is my 90-degree angle. I'll call this C. A is where I start, B is where I end. So this is side B. This is side A, and then this distance from the port to the ship is C. So I'm basically looking for the hypotenuse of this particular triangle. Now, some other information that I have here is how long I traveled. So from A to C, I traveled 3.5 hours. Well, I need to know the distance here. I don't need to know hours. So here, I need to keep in mind that distance equals rate times time. So the distance from A to C is equal to the rate, which is 22 knots, times the time, which is 3.5 hours. So that'd be 22 times 3 is 66, and then half of 22 is 11, so 66 plus 11 is 77 knots. I can also find the distance from C to B, because I'm traveling 22 knots times 4 hours is 88 knots. So this B is the distance from A to C is equal to 77. And then this A, which is the distance from C to B, let me see if I can clean that up again, is 88. So now I have some good information here. I have a 90-degree angle, I have my hypotenuse, and I know two sides. So I think I should be able to use the Pythagorean theorem to come up with that missing side. So I'm going to use the Pythagorean theorem. And that would say that a squared, or leg squared plus leg squared, equals hypotenuse squared. So 77 squared plus 88 squared is equal to that distance, that c squared that I'm interested in. So 77 squared is 5929. 88 squared is 7744. I like my variables on the left, so I'm going to flip that around, and I get c squared equals 13,673, and c is the square root of that. Now I only have to look at the positive or the principal root, and so c, after I find, so this would be the exact answer. The approximate answer would be 116.9316 nautical miles. So that would be the value for c here, approximately, because it's not the exact value. The exact value is the square root of 13,673. And then you would round that for however the directions in my math lab said. So a good picture is really going to be helpful here. Now, not everything has to do with bearings. Sometimes you just need to be able to write a good or draw a good picture to go with the problem that you're working on. So let's go ahead and choose another one to look at. See here. Okay, we always do heights of trees, so let's pick one of those. Now this one, they say see the figure, but I'm not going to paste the figure in. We're going to draw our own because I think that that's a good thing to learn to do. So Francisco needs to know the height of a tree from a given point on the ground. So he finds that the angle of elevation to the top of the tree is 36.7 degrees. Okay, so here we are. Here's some tree. We have to get a tree in here. And there's some point on the ground, and we'll assume that the tree is growing perpendicular to the ground. So we have a 90-degree angle there. And it says we have a 36.7 degree angle here to the top of the tree. That's the angle of elevation. Now we talked about angle of elevation and depression in our last lecture, so if you need to go back and review that, you can. Now this is the height of the tree that we're looking for. Now it says he then moves back 50 feet. So from this point, he moves back 50 feet. The distance from here to the original point is 50 feet. And now this angle of elevation is 22.2 degrees. And they want us to find the height based on what we have here. Well, I guess what we could is we could call this an unknown as an x, as this distance. And there's several ways that we could solve this. I think what I would like to do first is I would like to set up some trig ratios for the both triangles. So I have two triangles here. I have this triangle right here, the 36.7, and then I also have this larger one, not just this one on the left, but I have this one that goes all the way, the 22.2, all the way to the right angle and up. So those are the two triangles that I want to compare. So for the one, I'm going to just call this one the tangent of 36.7 degrees. Remember, tangent is opposite over adjacent. Okay, now for my next one, I want to do the tangent of 22.2 degrees. Remember, tangent is opposite over adjacent. Now this adjacent leg is not just 50, it's 50 plus x. Now what I could do here, we want h when we're done. So I could solve both of these for x, and we're going to have to do some pretty interesting algebra. I think it'll be fun. So if we solve both of these for x, I'm going to multiply both sides through by x, and here they'll cancel. And then I'm going to divide through by tangent 36.7 degrees. Tangent 36.7 degrees. So for this smaller triangle on the right, this right triangle on the right, I am left with x equal h over tangent 36.7 degrees. So x equal h over tangent 36.7 degrees. Now, for this other larger right triangle, the purple one that I have outlined here, it's not going to be as simple because I have a binomial in the denominator. And again, I want to solve that for x. Now, the reason I want to solve for x is I want everything left to have an h in it because I want to solve for height eventually. So to get started with this one, I'll multiply both sides through by 50 plus x. Got some fancy algebra here. These are fun problems. And I'm left with 50 plus x times a tangent of 22. So if I distribute that, I'm left with 50 tangent 22.2 degrees plus x tangent 22.2 degrees equals h. Now again, I want to solve this for x, so I'll subtract this across to both sides. So I end up with x tangent 22.2 degrees is equal to h minus 50 tangent 22.2 degrees. Now we want to solve for x, so I divide both sides through by the tangent of 22.2 degrees. And these cancel. So now I have x equal, for my purple triangle, let's get this in the correct color here, x equals h minus 50 tangent 22.2 degrees all over tangent 22.2 degrees. Now it might be tempting to think about that you might want to cancel here these tangent 22.2 degrees, but you can't because the tangent 22.2 degrees in the denominator goes under the h as well. So if you cancel it here, it is no longer under the h and it needs to be on both. So now what we're going to do next is I have both of these solved for x, and so I'm going to set x equal to x basically. So I'm going to set the x for the gray triangle equal to the x for the purple triangle, and I will get h over tangent 36.7 degrees is equal to h minus 50 tangent 22.2 degrees over the tangent of 22.2 degrees. So again, we're just doing a lot of algebra here. I'm trying to solve for h. So to get rid of these fractions, what I'm going to do is to cross multiply. And again, there's more than one way to solve these. So if you have a different approach that you would like to solve this ratio for, you certainly can. So when I cross multiply, I get h tangent 22.2 degrees equals. Now I have this tangent 36.7 degrees times all of this entire binomial, not just the h, but the h minus 50 tangent 22.2 degrees. Now again, I'm trying to solve for h, so in order to solve for h, I'm going to have to get all the h's on the left and everything that's not an h on the right. So I have h tangent 22.2 degrees. I'm going to take this tangent and distribute it, and I'll have h tangent 36.7 degrees minus 50 tangent 36.7 degrees times the tangent of 22.2 degrees. Okay, so let's copy this down. We'll start at the same spot on the next page. And so what I'll want to do is I want to move this tangent across. So I'm going to subtract h tangent 36.7 because I want all my h's on one side, minus h tangent 36.7 degrees. Now I can't combine these angles in any way. 22.7 and the 36.7, I don't subtract those. I'm subtracting the entire expression. Okay, so let's keep going on this. So I have h tangent 22.2 degrees minus h tangent 36.7 degrees equals negative 50 tangent 36.7 degrees tangent 22.2 degrees. Now the trick on this one is both of these have an h, so I'm going to factor out the h and I'm left with tangent 22.2 degrees minus tangent 36.7 degrees equals everything over here on the right. Now our final step is going to get h by itself, and the only way I can get h by itself is to divide by this difference on both sides. So whatever you do to one side, you do to the other. Okay, so these cancel over here. So finally, I'm left with h is equal to negative 50 tangent 36.7 degrees times the tangent of 22.2 degrees divided by tangent 22.2 degrees minus tangent 36.7 degrees. That's my answer. That's the exact answer. Now if we have to come up with an approximation for this, we plug it into our calculators. And this is where that fraction key is really going to be nice because we know exactly what's in the numerator and denominator when I use that fraction key. Okay, so let's pull the calculator in. Let's scoot this over a little bit. So here I'm going to use that alpha y equal so I can clearly see the numerator and denominator. So I have a negative 50 tangent 36.7. And again, I'm going to put degrees in there even though I don't have to because I can see I'm in degrees up here. It just serves as a reminder for me. Tangent 22.2. Again, I'm going to get rid of that extra parenthesis. It wasn't hurting anything, but I'm going to insert that degree, close parenthesis, arrow down, and then I have tangent 22.2 degrees, put in my degree, and then minus tangent 36.7 degrees. So that's second angle, degree, close. So I can clearly see numerator and denominator here, and if I hit enter, I get 45.09288. And then if this was in my math lab, then we would just make sure we looked at the rounding instructions to make sure we rounded it correctly. So here we get 49.092888923. Okay, so we were trying to find the height of something, and I think we were in terms of feet if I look back to the original problem. So that's one way we could solve this. There's a lot of algebra here, and I would expect that you would be able to do this algebra. You could have set this up another way first and solved for the gray triangle on the right and found the value for x, and then once you find that value for x, you can go back and plug it in to find the value for h. So it could have been a two-step process, but I just went after the single step. So is setting this up reasonable? Absolutely. You should be able to run through the algebra. There's quite a bit of algebra and there's a lot to keep track of, so don't try and fit this on like the bottom two lines of a sheet of paper because it's not going to fit. So we only got 3 problems done in a little over half an hour, but these are long problems. Make sure you spend a lot of time with these because these will definitely be showing up on the exam. As usual, if you have questions, just send me a text and a screenshot of what you're working on. I'm happy to help. Good luck.